Okay, and we're live. So it is October 30th, 2014, 11 a.m. Pacific, and this is DB Hangops. Today we're going to be talking about what's new in TokuDB, and we've got Tim Callahan to talk about it for us. And we're also going to talk a little bit about Outbrain's Orchestrator. We had a demo of it previously, and so hopefully we can, I think John was going to give some demos on it or stuff too. And give me 1 second. Just realized I have the YouTube stream playing somewhere else and it's confusing me. There we go. Okay. And yeah, and then we'll kind of go from there. So quick round of introductions. I'm Jeff. I'm a DBA at Box. And how about we go to you, Jeremy?
Jeremy Tinley. I'm a senior ops engineer for Etsy.
Okay. John?
I'm John Cesario. I'm a DBA.
And Tim.
Hi, I'm Tim Callahan from TokuTech.
Okay, so actually, why don't you go ahead and kick us off, Tim, since you got your screen share all set to go.
Excellent. Can you see it okay?
Yep.
All right. So in TokuDB 7.5, we introduced a new feature we call read-free replication. I think I dreamt up that name. I don't have a future in marketing, but what I like about it is it's kind of self-documenting and really explains what we're trying to get down to here. So just in case someone looks at this stream standalone, I want to make just a quick slide about, this is what TokuDB is. We're a transactional MySQL storage engine, so we try to compete or replace InnoDB in people's implementations. We ship from our website directly a MySQL 5.5 and Maria 5.5 version. We worked closely with Percona for a good long time to create a Percona Server 5.6 version. Internally, we do builds on Percona 5.6 and MySQL 5.6. We just don't offer those yet. We also have MariaDB 10 versions that are available from Maria directly. Again, we build and test them here as well, but not commercially supporting them or making them available from our site yet. To compete, to be transactional, certainly we've got ACID and MVCC. We've got a free open source community edition. If you want to come look at code, FT Engine is our Handlerton code. Then the fractal trees themselves are in a separate repo. Easy to come, easy to build, and get started with it if you like to build your own. And then we have an enterprise edition which has commercial support and a feature called Hot Backup for taking online backups of running servers. But the three main goals of TokuDB have always been at the bottom here. It's about performance, it's about high compression, that's always on, not optional, and about agility, so hot schema changes. And if you want to learn more about those features, certainly plenty of good information at the website, but nothing I wanted to spend time talking about here. So before we get into read-free replication, I need to do a few things. I want to set the table on what a B-tree is and how it differs from a fractal tree, because we couldn't go read-free without a fractal tree. So just a 5-6 minute understanding of how fractal trees differ from B-trees. A couple slides on how replication works at a very high level. I'll argue it's very hand-wavy, but I think it gets to the point of why read-free replication is important and how it can help. And then right into read-free replication, some ideas, some benchmarks, and some potential configurations that it might empower in people's environments. So briefly on B-trees, if you go to Wikipedia, you'll probably see a picture very similar to this. Most databases rely on B-trees for indexing. InnoDB uses them. MyISAM uses them. Other databases use B-trees as well. But the basic idea in a B-tree is this. It looks like a pyramid. At the very top, you have what's called a root node. Underneath that, you have other nodes that are called internal nodes. And those are about pathing and about being able to get to data quickly without having to visit every node in the tree. So there's pivots to support that pathing and pointers. And then at the very bottom, you have what's called a leaf node. And this is generally where the actual data is going to be stored. And within those leaf nodes, it's sorted from ascending or descending order, so that when you get down to the leaf node itself, you can quickly get to the data you're looking for. So for a quick example, if we were to fill out a B tree and all we were going to store is numbers, you can think of these as key value pairs. So if I had an index in InnoDB, for example, and I indexed my primary key was just an integer, then these numbers would represent the key, the integer column itself, or the auto increment. And what you'd actually be storing alongside this key is a value or a payload, and that payload is the rest of the row in InnoDB. So in this example I drew, my rule is greater than or equal to, which means as I'm going through this tree, I look at the number in the node, and if what I'm looking for is greater than or equal to that number, I go right. Otherwise, I go left, which makes a really simple example here. If we want to search for something, for example, if we want to know is 25 in this B tree, we go to the root node. 25 is greater than 22, so we go right. We then compare to the 99. It's less than 99, so we go left to that left pointer. We end up in the leaf node, and then we do a quick binary search since it's sorted, and we can get to 25. So operationally, we've had to visit 3 nodes, and it's pretty efficient to find the number 25. If we laid this all out in an array, for example, if we sorted it, it would be very expensive to sort a very large array. If we didn't sort it, you'd have to scan potentially the entire array to find things. Insert is similar. You do a search path to get down to the leaf node, and when you get there, you stuff in what you want to add. So in this example, if I wanted to insert 15, I go left at 22, I make a right at 10, I get down to the leaf node, I notice there's a 10 and a 20, I inject 15 right in the middle of that to keep it sorted. So very high level, very, I think, easy to grok and get your head around, get an understanding. But this is essentially how B trees work, and B trees are the underpinnings of most databases. So I think it's kind of interesting to be thinking about these things. But B trees were invented in the early 70s. In the early 70s, it was hard to imagine these gargantuan data sets that we have today. So very good data structure. The data structure itself becomes challenged when that B tree is entirely in memory. It's awesome. The insertion properties, the search properties, it all works really, really well. The challenge is when you've got more data than RAM, which is common with these B trees, or with data in general. So rather than being at memory bandwidth, which is crazy fast, you end up being I/O limited. Spinning disks, Fusion I/O, whatnot, they certainly have different characteristics, but getting data off an SSD, while much faster than a spinning disk, is still much slower compared to RAM. So what you do with a B tree is you keep as much of the tree in memory as possible. Generally, the goal is keep all the internal nodes, everything but the leaf nodes in memory if possible, because that means every time you go to do a lookup, you do at most 1 I/O. The challenge there is when you go to do an insert, you're I/O bound as well. But in this example, you can see, we have enough memory for the internal nodes, and let's pretend our cache was such that we could only have 1 leaf node at a time. So if we were searching for the value 3, it's a fully in-memory query, very fast. If we were searching for 25, we'd have to wait for an I/O, retrieve that block off disk. It probably has to be deserialized, brought into the cache table. A lot more overhead, so you become quickly I/O is the performance blocker here. So let's think about how we might be able to do that differently. And Inno has done something that we'll talk about in a minute. But so a fractal tree index, if you look at this picture right here, it looks similar to a B tree. The big difference is these message buffers in the upper levels of the tree. So the root node and the 2 internal nodes in this example have message buffers. So our similarity to a B tree is with a fractal tree index, we're going to store the data in the leaf nodes when it finally gets down there, and we're going to use this index key for ordering. So we're going to have pointers and pivots, and we're going to search down the tree just like it's a B tree. 2 big differences are, one, these message buffers at the top, and we'll talk about what they enable. But the other one is there's characteristics about how this data structure works such that we can blow it out and have much bigger nodes. So if you're an Inno fan, traditionally InnoDB uses 16K blocks or nodes here. I saw patches, there's a labs release in MySQL 5.7 where they're going to support 32K and 64K. It's still getting bigger. Our blocks are even bigger, they're 4 megabytes. But what these really enable is when you're doing range queries, you get a lot more data co-located. So with a single I/O operation, you bring back a lot more useful data. So our 4 meg, completely variable. You can, if you want to behave a lot like Inno, you could set it down to 16K. It defaults to 4 megabytes. You can make it 12 megabytes if you, depending on your table. And this is definable at the table level. So some tables you can use smaller and some larger. But if you follow this path on the right here, all these internal nodes, they have message buffers. So as we're doing operations, we don't necessarily have to go all the way down the tree to do the work. We fill up these buffers. As they overflow, they cascade, kind of like a waterfall. And then they cascade and cascade. And when they finally hit the leaf node at the bottom, when there's enough overflow, we apply the messages to the leaf node. And behold, it operates just like a B tree all over again. So to see that an example of that, the first thing that might come to mind is, and I was fascinated by this when I first started with MySQL. Well, I was wondering to myself, InnoDB has this thing called a change buffer. I think it was introduced in 5.1. I think it was insert only, and then in 5.5 it got renamed to a change buffer because it also supports updates and deletes. And so yes, InnoDB has this change buffer. Couple caveats. One is there is no buffer on the primary key index. That is an unbuffered B tree. But for each secondary index, there's just one big buffer, and I think that buffer can get really large if you read the documentation. It can grow quite large. But what's interesting is if, I'm a benchmarker at heart, so I like to run and see what happens. Well, so these change buffers, if you look at these two graphs here, this is II bench, so indexed insertion. I got an auto incrementing table where I'm incrementing 3 secondary indexes that are random. And if you look at the two graphs, it's interesting. So the blue line here is when the change buffer is turned on, and as you can see, it's a really nice property, right? The insertion performance stays for a lot longer and stays better for longer. And with turning off the change buffer, when performance collapses at around 110 million inserts, you're completely I/O bound because every insert operation is requiring several I/Os. But what's interesting to note on the blue line is, so this buffering, it's amortizing I/O, meaning occasionally I'll have to do an I/O to help flush some of these buffers. And one of those I/Os I might satisfy several inserts, may call it a dozen, call it 50. But over time, when the data gets large enough, that blue line will become the red line. So the bigger your data, the less this change buffer can help, just because of the properties of the index itself. So it definitely lets your server hold on for a lot longer, but eventually the lines end up almost collapsing on themselves. So if we look at a fractal tree index, in practice here, same as the example as before. I've got the tree filled out, 25, 10, 99. Looks a lot like a B tree. The buffers are empty because I'm just getting started. When I go to do an insert, instead of pathing down the tree and working my way down, I can simply inject a message in the root node, an insert message, 15. And if this were a table, it would be 15 is the primary key, and the payload would be all the other column data. So down the bottom, search operations, same rule as a B tree. I have to go all the way down the tree. But as I'm going, I'm going to also peek in these buffers to see if messages in the buffers are affecting what I'm looking for. So if I did a search for 15 after this was committed, I'd want to 15 counts because there's a message in the buffer for the value 15. These messages cascade down the tree as the buffers fill up. Eventually, they apply to a leaf node. The nice property here is when it's time to bring it to the leaf node, I do one large I/O, and I do several operations, potentially thousands of which, a bunch of inserts, updates, and deletes, all for that one I/O operation. The other interesting property here is Fusion I/O is fast. SSDs are faster than spinning disks. No matter how fast your I/O is, there's still an operational cost to peeling data off of a storage device, and part of that cost is by bringing it into the cache, I have to bump something else out. It's going to require CPU to serialize and deserialize this data. So it's not that these some of these extremely fast I/O devices eliminate these I/O problems. They just change things. You change the cache properties example of your system.
Hey Tim, I have a quick question.
Mm-hmm.
So when you're doing these insertions, how big is that message buffer that you have there? Is that where that 4 megabytes come in, or is the 4 megabyte the node and message buffer?
Nope, that's a good question. So if we drew this to scale, the root node itself at the very top there, where I see that the 25 is what I'm using for a pivot, and I've got 2 pointers, and then I have a buffer, right? That entire that is in and of itself entirely one node. So 4 megabytes by default is everything up there. And our fan out isn't, for an example, it's nice to show a fan out of 2, right? I can only go left and right. Well, in reality, our fan out, InnoDB, I think, is probably similar. The real fan out is 16. So I've got 16 pivots, 17 pointers, and then therefore I have 17 of these buffers. So each buffer is probably 128K because the buffer is actually only is segmented out into the direction down the tree it's going to head. I don't know how confusing that explanation was, but in essence, so that very top level, that root node, it's 4 megabytes in its entirety. It's made up of 17 message buffers because the fan out is actually 17. So for this example, the buffer, if I had a fan out of 2, like I show here, I'd have negligible number of bytes for pivots and pointers, and then each buffer would be about 2 megabytes.
Got it. Thank you.
Sure. The other cool thing about fractal trees and these buffers is these message buffers are very generic, and it's up to our imagination to decide what we're going to do with them. So as originally developed, it was, okay, we need to support like key value operators. Well, for key value, all you really need is insert and delete, because update is actually delete then insert, right? So you needed the initial implementation, we just needed an insert message and a delete message. Over time, we decided, we can use this buffer for other interesting things. So for agility, we have a message called add column. So rather than rewriting the table, we inject a message in the root node called add column, and in here we said, hey, I want to add column C4, it's big int, default null. We just drop a tiny message in the top of the tree, we're done. User gets right back to work. Table doesn't have to be rewritten, because if the next user does a select statement, we just come down the tree and we notice, oh, there's an add column message. So when I materialize the row back to the user, I'm going to append a column C4 to that query. And if the user wants to update C4, that's fine too, because we see this message. So agility messages exist, as does the next one here, increment. We have the ability to do a fast update, which means if the caller doesn't care that that update actually hit a row, if they're not interested in success or failure, we can accept that message and apply it, in a deferred manner. It doesn't matter what that +5 does until someone comes along and says, hey, what's the value of that column in row 22? So anything can be a message. It's really, we do drop column, add column, expand column using messages. We do fast updates. And that's really a lot of where the magic of read free is going to come from, is these message buffers. So really what TokuDB is, take MySQL, take Maria, take Percona, add the power of fractal tree indexes. That's what we call TokuDB. I want to do a couple minutes on MySQL replication. This is MySQL replication 101, but definitely enough I think you need to understand to be able to understand read free, which we're a few slides away from. So for MySQL replication, there's basically 3 modes, and the replication operations get logged in the bin log. The modes are statement-based, row-based, and mixed. So statement-based is statement gets run on the master. Statement executes when committed. It goes into the bin log. That exact statement, the statement gets shipped over to the slaves and gets applied. So an example of where I think that's a really good thing is they're very compact. If I'm doing an insert into table, select star from table, just that amount of text needs to make it into the bin log and get shipped. If bar had a billion rows and I did that row-based, that's going to be a lot of information going into the binary logs. Row-based is interesting in that with row-based, what happens is you might do that same insert into foo select star from bar statement, but with row-based, the before and after image of every single row that got touched is going into the binary log. So on an insert, you only have to show one side, or on a delete. But on an update, you're going to have the before image of the row and then the after image of the row. So an example there would be, if in table foo I updated a row from 1.1 to 1.2, then I end up with something that semantically looks like that. It's encoded differently for compactness, but I think you get the point. And then, sounds like someone has an open mic.
That would be me.
Okay. And then lastly is mixed. Mixed is it defaults to statement unless MySQL can detect that what you're about to do is unsafe as a statement. And a quick, easy to understand example is do an update statement with a limit without. I don't know if you can put an order by on an update statement. I always look at these and I'm always a little bit weirded out because that statement makes me nervous. Coming from my background at VoltDB and determinism in databases, where you never want to have something non-deterministic happening. So I'm sure there's use cases where unsafe SQL makes sense. Haven't run into too many of those myself. So in MySQL replication, there's also this concept of a read-only slave. So on your slave, if in your myCNF, you set read-only equal to 1, slave goes in read-only mode, which I think is great. If you're just throwing queries at it, there's no need for people to be doing insert, update, delete operations. There's an exception there. Anyone with superpriv is allowed to insert, update, delete directly. I will definitely give you a warning with us. If you do that, you certainly have given yourself the ability to break this read-free replication feature, and you'll understand in a minute why that is. So replication, the slave apply. So on the slave itself, again, this is a little hand wavy, but I think enough information to understand. What's happening is the slave it's reading a replication event from the binary log. If it was done in statement mode, the statement gets executed on the slave via SQL. If it was row-based, there's one of two things that's going to occur. If it was an insert on the master, it's just going to write the row, and I say that in that it's left to the details of the storage engine what write the row means. So TokuDB, our interpretation of write the row could certainly be different than InnoDB's and MyISAM's and ARIA and others. If it's a delete or an update statement, a lookup is induced first through the storage engine. And the reason being, it checks to see if the row doesn't exist, and if the row doesn't exist, replication stops. Like many other things, I assume there's probably a parameter to relax that behavior, but that's the default behavior. And then the last important thing here to talk about is slave lag. So in MySQL 5.5, replication is single-threaded. You can certainly be extremely concurrent on a master, but slaves are applying the replication stream in a single-threaded fashion. Can certainly cause slaves to lag behind the master. There's improvements in 5.6 that's built in for multi-threaded slaves. Maria 10's got some interesting parallel replication mechanisms. It seemed a lot more complex than for me to try to do much explanation on that. The good news is our read-free replication benefits from those as well. So not only do we really like what we've done with RFR, but those technologies themselves, there's no reason that they're not also going to be compatible with read-free replication. And as an example of that, we're already in Percona Server 5.6. The upcoming there's a release coming out in the not so distant future where they've added support for read-free replication to their to the GA build available from Percona. So here we are, read-free replication itself. Just a couple quick requirements. One, on the master, you got to have the bin log format set to row. The whole goal here is to not induce read behavior on slaves. The only way that can be done is to know before and after images. So with a statement, there's no way for us to kind of fake the fact that an update needs to take a dip and look at the row to make a change. So it's only available when your bin log entries are row-based. On the slave, you've got to do a couple things. One is put it in read-only. We decided to check for this just as a safety precaution. SuperPriv is still allowed in, but we figured it was better to at least check this. And if a user doesn't have read-only set for one, then read-free replication won't apply regardless of the next two settings. And then there's two settings. One is whether or not we want to relax unique checks, and the other is if we want to relax the read, modify, write behavior of replication. Skipping unique checks, what you want to do here is disable this repl unique check flag. It's okay. Why is it okay? Well, it's okay because the master already performed this uniqueness check. So if I'm doing an insert, for example, and I've got a secondary index that's unique, or my primary key needs to be checked for uniqueness, the master's already done the work. The slave can benefit from the fact that that work's been done. It doesn't have to do it as well. There's an interesting reason why Inno can't skip a unique check, and the answer is that it could. However, since it doesn't support change buffering on the primary key, it has to read the row anyway for maintenance. So reading the row for maintenance and then not also taking a quick peek since it's already in memory, I think there's a marginal improvement, and I believe there actually is a uniqueness checks my CNF parameter where you can relax it permanently if you wanted to. But I've done some measurements. If you have to do the IO is the outlier in the process. So relaxing it doesn't really save much if you still have to do the read. The big optimization is about skipping this read, modify, write behavior. So there's the setting on your slave. Why is it okay? Well, if it's row-based, the master has provided us the before and after row images. So it's actually done the hard work for us. InnoDB can't skip read, modify, write, and the reason being the same as the unique check. The primary key doesn't support change buffering. So we have to do that IO anyway. We've got to do that read. The secondary indexes have change buffers, so you can definitely defer some of from the IO in secondary indexes. But the real pain here is going to be looking up the PKs themselves. TokuDB can skip read, modify, write for two reasons. One is everything we need to do, it's in the binary log. The other is it's just simple message injection, which is why I did that. The early part of this to talk about fractal trees. We're just dropping messages in buffers. There's definitely no need to do the I/O to bring the block into memory to actually do the modification. One quick benchmark to kind of help explain and show what's going on here. So this is a classic I/O-bound sysbench workload. So my cache, I'm using direct I/O. I'm using a 4 gig cache. I'm loading about 35 gigs worth of data. So I'm completely I/O bound on this sysbench workload. And then there's two lines here. The master in this process is the blue line, and it's cruising along at around 175 sysbench transactions per second. And the red line here is the slave. What I'm measuring is commits per second, which is also equivalent in sysbench speak to transactions per second. So even though, and this is with 64 threads on the master for concurrency, even though the slave doesn't have to do the read portion of sysbench, it's getting crushed by the reads it has to do to keep up with the master's insert, update, and delete traffic. So even though the master's at about 175 commits per second, the slave's at about 75. So every second into this benchmark, the slave is falling about 100 commits per second behind the master due to the lack of concurrency on the secondary, on the slave here. Read-free replication is completely dynamic, those two server parameters. So on the slave at around a little over 10 minutes, I enable read-free replication on this slave just to show what happens, and you get this amazing looking peak where we can see here that this slave, configured as is actually capable of about 1,400 commits per second when it's running read-free. And then as soon as it catches up, the line quickly drops down and the red and the blue line are pegged. There's absolutely no lag going on in the server at that point. The line basically becomes purple because the two lines are merging into one. So there's no lag on this, which is nice. We've eliminated lag with read-free replication, but it's about more than just eliminating lag. So the slaves are now keeping up with masters in this example. A couple more interesting things to look at. Same master-slave comparison here, but here we're looking at I/O utilization. So the slave was lagging in the prior slide, commits per second. While running the master, this is a kind of a nice graph as a benchmarker. I'm 100% utilizing the I/O on my primary. On my slave, I'm at about 85, almost 90% I/O utilization before enabling the read-free replication at just after 10 minutes. Once it's enabled, I/O utilization drops to about 18%. And what that's showing is that's additional read capacity. There's so much less I/O going on in that slave, it can handle many more queries for read scaling if that's what you're looking to accomplish in your environment. So this is just looking at overall I/O utilization. The last thing to look at is let's look at reads and writes directly. So I/O utilization is kind of a blend of the two. So here again, this is just the slave's I/O. My writes per second is in red. And as you can see, it's hovering around 2,000 writes per second. It spikes on the catch-up phase to over 6,000 writes per second, and then it settles down back to around 2,000. And these writes are a couple things. This slave is running completely durable. So the relay log.info file is getting f-synced with each commit. The master.info is being f-synced at each commit, and TokuDB itself, our logs are getting f-synced at each commit. So that explains why there's so much write I/O going on. But what's also interesting is as soon as we enabled read-free replication, you can see there reads are pretty much disappearing. We're almost down at 0. The other thing here is to think about the expense of these reads versus these writes. So even before turning on the optimization, the red line is mostly f-sync traffic. So these are tiny little f-syncs completely being absorbed by a caching RAID controller. So the blue line down there, those reads per second are real. That's actually 5 millis going out to disk, peeling something off of disk and bringing it in. So as you can see there, lots of interesting things are now possible. And just a couple more idea slides, and then I'm happy to answer questions. So idea number one is just scale your reads. And I think master slave is great. It's nice having a slave around to step in should the master fail. But while you're waiting for that to happen, if it ever happens, scaling your reads, I think, is really cool. So if we bring your I/O utilization down as much as we had, above the line, that's kind of what TokuDB looks like without this optimization. If and when you enable it, you can certainly send a whole lot more readers to your slaves and be getting query responses back faster than you would without the optimization. So I think that's kind of an obvious one, scaling reads. Another option is this, shared slaves. So in the top example, I have a slave for each master dedicated. I might be able to get away with grouping up. So have a single machine serving as a slave to master 1 and master 2, just because there's so much less I/O utilization required. The key here is to make sure slave 1 plus 2 is probably also there for HA purposes. So you certainly have to make sure you don't collapse too many boxes onto one slave and don't leave yourself enough capacity to stand in as one of those masters if needed. And then the last one is just decide how you're going to spend your budget. You might be doing a lot of I/O on your masters, and go buy flash, go buy PCI Express cards, but you might be able to get away with some simple SAS or SATA on your slaves, or on some of your slaves at least, and save yourself some real money with respect to storage. So that's it. Happy to answer questions that you guys might have.
Okay, let me open up the camera. Sorry, one sec. Go ahead, Shlomi.
Yeah. So first of all, this is very cool. So you say you're saving a lot of I/O and CPU by skipping stuff that you just know you can skip. Is that the basic idea? Did I get it right?
Yes.
Okay.
Yeah. So basically, we did this TokuMX in Mongo. We done this when we first implemented it. In Mongo, secondaries are not allowed. There's no super get around it and do some writes. So part of what's going on here is trust, right? The master did the work. The master guaranteed uniqueness. The master gave me the before image of the row. If I feel like I can trust the master, then I can save myself the effort of double checking its work.
It's pretty cool. I never realized this would save so much time.
Yeah, and what I look to, part of the feedback I was hoping to hear a little bit from you guys is, one requirement has to be row-based replication. And I'm sure some places that's fine, some places it's not a problem at all. There's going to be use cases where it's just out of the question. So I'm always happy to hear your guys' operational experience with how much RBR is there in the world, or how much SB statement based is there, and why.
Yeah, I'm willing to jump on that one, and so we're in the process of getting rolled out to 5.6 and also turning on RBR in a few places, and there's definitely some interesting learnings when you turn on RBR and some configs you need to be cognizant of. But one of the more interesting things, though, was when we do query kind of analysis off of the binary logs, or just kind of looking in there to triage issues, being able to have the statement inside of there. And so as a result, we found we had to enable, I can't remember offhand, but there's an option with RBR where it also writes the statement into the binary log. And so it actually causes the binary logs to get a lot larger faster, and we had to turn down our retention because of it. But provided you have that, effectively getting your statement and the row change, then you can, turning on something like read-free replication where all it needs is the row image to make a decision, and still having the statements there in a commented format that's available for operators to get at. I mean, it would make it valuable for sure.
Okay.
This is definitely, I really want to try, throwing the Toku server in one of our, as a replica in one of our clusters, and just kind of see how it looks. This kind of read capacity stuff is very interesting. Yeah,
and the other interesting thing there is, my screen still sharing, or is that off now?
It's off. We can see you.
Okay. So the other interesting thing is, right, one thing I like about MySQL is replication is above us. We're just an engine to MySQL. So you can certainly try out a TokuDB slave with an InnoDB master. There is absolutely no reason. That doesn't matter at all. The other interesting thing is, even though you don't want to be doing CRUD behind the scenes on the secondary, on the slave, you can certainly have a additional more or less indexes on the secondaries, and read-free replication is fine. The code takes a peek and it's like, oh, it doesn't rely on the fact that the master has the same exact indexing scheme as the slave. So if you want to have more or less indexes, that's fair game as well.
Yeah, so something else I was curious about, you had mentioned that if a record or something is inserted on the slave using the super privilege, that it would break this. And I'm curious, like, what does that look like? Is it more, it's a question mark, like it could break it if a certain condition happens or a certain field comes in? Or is it, if you do it, Toku will detect it and like kind of block that or something?
Okay, that's a good point. Yeah, break, to me, break means if you want to have table 55 on your slave that's just there for your own operational purposes, have at it. What you'd never want to do is if you manually put a row on a slave and then that same row came over via read-free replication, we wouldn't do the uniqueness check. So we would blindly be putting a second row in a table with the same PK. And I think MySQL has a uniqueness checks parameter, and right now you could do that too, right? Really weird things can happen at that point because then when you go to do an update, it's only going to look for one of them, and now you're going to have like two of the same PK. That's what I mean by break is you've broken the kind of the contract that there's determinism between these two boxes. But nothing, it's not going to detect it. It's not going to check it and be like, whoa, something weird is going on here. And that's the overall goal, right? We're blindly accepting the work from the master and applying it to the slave.
So that's interesting. That means situations where you would have effectively a duplicate key warning coming up through replication. So if let's say you have a master-master pair, and for you're in a transition state where you're transitioning traffic from one to the other, and since they're master-master, statements could potentially be going both ways. And if you have a statement run on both, and this kind of feature is enabled, that could lead to some very interesting cases to worry about then. At least, at the very least, something that you would want to be running a tool like PT table checksum or something to kind of make sure that things are in a good state.
Exactly, and PT table checksum was, certainly happy to give it a plug. It was the primary test tool we used for this feature. We beat up as many primary masters as we could with slaves attached, with RFR on off, change this, change that, and then we just stopped and ran PT table checksum to make sure everything was solid. It was a great tool for testing for us.
Yeah, so actually I'm curious for other folks on the call here, how many of you guys are running a master-master replication topology? Because that actually does sound like the one kind of case to be concerned about with this kind of feature, based on how your traffic pattern for switching between them works. And I mean, this is one of those things like with 5.6 and using things like MySQL Fabric and the more durable replication, you could get around this and not need master-master, but if you currently have it.
Yeah, we run master-master today, and that would be a bit of a challenge. I mean, we're kind of stuck in that architecture for the moment. So I was actually looking at whether or not we could use this for consolidated offsites, like you pointed out in the slides, where we could say, let's compile 4 or 5 instances. Challenge for us then would be moving off of statement-based to row-based, because it all have to be done on our master.
Yeah.
We're using master-master replication, but just because we really have to at one location, but in other ways is not our preferred way of doing it. Sorry, John.
Oh, no worries, no worries. I'm going to have to go with everyone else's answer and just echo that, and that saying that almost everywhere I've seen uses master-master extensively for either, more mature companies, I think, do some more advanced stuff, but I think the vast majority of setups I see when it comes to failover and HA topologies is an IP failover between 2 co-masters. I think that'll probably get a lot simpler as we move towards GTIDs and Fabric, but for right now, that's really the standard deployment I've heard about almost everywhere that is in an extremely mature shop. It's just simple to deploy. There's things like PRM or MHA out there, and MMM to help manage that. So it's really common to see the master-master setup. I'm not sure anyone I know could actually get around that. And even more so, I see it commonly not just for local clusters, but using it in combination with semi-sync to do geo-distributed masters, for example, 2 data center locations or 2 Amazon regions on separate ends of the earth, with a replication using link using semi-sync between them, and then something abstracted out to manage it. So one way or another, even in the more mature shops, I see MM happening. Something like Orchestrator could certainly help with this, though.
So something I was actually going to ask too was, Tim, those two variables that you would set for the uniqueness checking in TokuDB's read-free replication, are they dynamic variables, or do you have to restart the server to get them?
No, they're dynamic.
So maybe that actually is a case then. So you could probably get away with running master and actually don't have those enabled, so you won't get the read-free on your master topology. And then whatever process or scripts that you have to move your replicas around or change things around, part of that process is then turning that variable on or off based on, are you going into a read-only replica state, or are you going into a passive master state? So okay, it does sound like it's still kind of viable then, because that was my big concern was, running kind of mixed configs is sometimes a little concerning or confusing. And then if you have to juggle things around in topology, it even gets a little more challenging. But if the variable's dynamic, it definitely makes it easier to do.
Generally, when I've the main, I mean, a read-free replication sounds amazing, but in the most, I don't hear about TokuDB coming up as a like, people don't ask me. I mean, I try to mention it, but when I really mention it, the features that really are the main selling points when I hear about them is faster bulk loading, like the really write-heavy ETL type stuff, and compression. Those are the massive selling points because it is definitely a weakness. I know so many people who do data warehousing just using InnoDB, and it gets extremely painful once you start talking about terabytes and terabytes of data. And the more efficient compression and write capabilities and bulk loading capabilities of TokuDB are definitely its main selling point. Whereas the drawback is hot backups is what we usually come with. Well, we'd love to use it, but we are either going to need to buy extra hardware to be able to take backups regularly, or we're going to need to evaluate putting something recurring into the licensing budget, which really doesn't matter what company you're at, is always a fun discussion in my experience. So, like, yeah, I guess my point would be just that's really awesome. Read-free replication is awesome, and I love the idea that you could have the expanded bandwidth for that to add it. But like read scale out is not like the first use case I hear with TokuDB. It's always about the data warehousing and being able to cram like 2 terabytes of data into a database every single night, like with as fast as possible. And the faster we can get it in there, the better, because it's going to keep scaling up. Every day, every month, we're going to be adding gigabytes and gigabytes and gigabytes. So we have to keep doing this, and we don't. And whatever reason they have, these companies want to stay on MySQL. There's an ease of use of having that ad hoc query capability that's very fast compared to Hive or something else. Or it's the devil right? So the idea that you have MySQL, but you also have these an engine geared towards ETL is the main selling point that I both pitch and I hear about when I talk about TokuDB.
Cool. So any other questions for Tim around read-free replication or Toku?
I have some being farmed, but they may have to wait and be tweeted until after DB Hangouts. So, but I have people messaging me and saying they are interested in it.
Is Shlomi back with us?
I am. Sorry, my laptop ran out of battery and crashed. So I was dual monitoring with my iPad. Yeah. So yeah, that sounds pretty awesome, Tim. Yeah, good work.
Thank you.
Yeah, very, 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 very cool feature. If only we could get it merged into main.
Well, there was a storage engine summit again this year, so there's always hope. And every year at the Oracle MySQL Storage Engine Summit, when they go to the end where they're asking for other comments or questions, I said, "Is this the year we can be included as an engine with MySQL?" And then there's always some giggles, and we move on to the next question.
Okay, it looks like Hangout just punted me for about a minute, and I think it just happened to John too. Is everyone still here?
We got 2 Johns and 2 Jeffs. Like the Brady Bunch down there. Look at that.
Look, yeah, I can put him to work. Where's my clone? He's got ops work to do.
It's just like me and Jeremy are the sole survivors at the moment.
Alrighty. So the last thing I'd ask was, yeah, were there any other questions, or do we want to jump over to talking about Orchestrator for a little bit?
I think.
Good to do Orchestrator?
Shlomi, you ready?
Yeah, I'm good.
All right.
You are leading the conversation.
I am. I am. Do you have a screen share, Shlomi, or should I?
Yeah, I do. Just a sec. Let me see that this works. I'm on Linux, so. There it is. Can you see it?
I don't know how to own the camera.
I've pegged it on the camera on you, Shlomi, so you've got the floor.
Right. Have you got it? So can you see me drag in and? Okay. So this is the basic how Orchestrator looks like. This is a topology I set up on my laptop. It's a MySQL sandbox. It's just a local dummy instead. It's pretty much like that on production as well. So I have this master right here, and it's got 1, 2, 3, 4, 5 slaves, and yet another slave for one of those slaves. So I've already demoed this a couple of months back, maybe 3 months ago. Apart from visualizing your topology, which is in itself valuable, Orchestrator is also able to help you out in modifying your topology. So if you want to make this server a child or another, you just drag it over. Things are pretty slow because of the switch check, so my CPU is really burning. Orchestrator is going to say, are you sure you want me to add? I say, sure, please go ahead.
Hey, Shlomi, can you still hear me?
I can hear you.
It sounds like you're really breaking up. We might actually need to pass over to John, see if he has a better connection right now.
Test 1, 2, 3. Echo. Am I better or no?
You seem a lot better to me, John. Yeah, Shlomi, is your connection okay?
Yeah, I can hear you. I'm going to stop the screen share.
Okay.
So actually, why don't we have you bring up the screen share, and we'll just and then I'll just blurb about it real quick, and then you can kind of move some stuff around it. You can be the mouse on it, because you've got a much better setup than I do. I've only got 3 nodes. I can kind of make fun. So let's show me. Yeah, can you bring up your screen share again, and let's go to the clusters page, the cluster dashboard.
Sure.
We're gonna be. It's gonna be awesome. We're gonna work in tandem. It's gonna be teamwork. The MySQL community working together.
Okay, there it is with myself now.
Oh man, Shlomi, your audio is very grainy, but yeah, no screen share yet.
I think he's still. There we go. I think it's coming up.
There we go. There's the screen share.
Perfect. Okay. So we're talking about Outbrain Orchestrator. We have the author with us, Shlomi, and we've and probably know him from OpenArt. This is the Outbrain Orchestrator, released a little while ago. It's been growing very fast. It's written in Go, which is a lovely language, and people should be checking out for their Ops work as well. And so what we have here is a live replication topology. There is 1, 2, 3, 4, 5, 6, 7 servers, right? And so what we have is a two-tier nested replication topology. For example, maybe you're evaluating TokuDB. So you've set up your 2 slaves under under your main set of slaves in order to test write flow through them and maybe leverage read-free replication to see how much extra bandwidth you could get in there. And Outbrain Orchestrator is getting a lot of flexibility, but the main purpose that I saw it initially created for, at least, and someone can correct me if I'm wrong, is managing some replication topologies. Like, say, for example, you want to take one of your slaves and promote it to a co-master. It can be as simple as dragging and dropping. Let's see if this works. Let's see, refresh here in a second. So, right. So I don't know how many of you have also written those hundreds of deployment plans to jump a slave back and forth and to promote a slave to a master or to another slave or not. But it's that simple. It, for the most part, just works as far as I can tell, although more exposure will certainly find outliers and things that we can improve. And what we're looking at right now is every single instance has some basic information grabbed about it as well, and some basic actions as well you can take. Information about certain replication settings. There's also functionality in there to set maintenance windows, so I could certainly see Outbrain Orchestrator becoming a HUD or a heads-up display for every single person's large panel TV on their DBA team as a basic monitoring system. It shouldn't be that hard, especially with some of the new features like the agent as well. Shlomi just released this with recent versions, and what the agent is capable of doing is working on every single server and provides command line interfaces and interactivity with all of the servers in the cluster. For example, what you just saw was a slave being promoted, but you could also handle this promotions or demotions through the CLI as well, so huge opportunities for orchestration. The agents go even one step farther, and Shlomi has released functionality to allow an LVM snapshot to be taken on one server and moved to another server. That's tremendous, right? Especially with the CLI interface. The frameworks that are normally having to be built in order to pass snapshots back and forth are huge, and I'm sure everyone's tried to do that and found nasty, nasty things of SSH keys and horrible kludges with expect and Perl and other terrible things. And this just takes it and provides us a very clean API interface to be able to do this. And not only that, the agent is pluggable. So what I would love, PRs I'm sure are accepted, and I know I'm trying to do it myself. Extra backup should, you could take an extra backup snapshot, your own custom snapshot functionality, various other ways could be integrated into this agent system. Not to mention, like, you could have eventually hooks for your application center to be able to say, take this slave out of rotation using reaching out to your external service like Consul or Zookeeper or whatever. Really, really powerful stuff, and everyone should take a look at this. Let's see, what else can I talk about here? Oh, sudo GTI demode, which was an interesting blurb there. So let me just check out his blog. I'm sure Jeff will be fetching a URL for the blog right now. Sudo GTI demode is a very interesting implementation of GTIDs using, I believe, the comments in DDL and table schemas, and to create in a way for us to recover failed slaves and find a point in time to recover from. So, for example, if you're running a 3-tier replication topology with one slave head hanging off of a B node, and that B node fails, you could take your C node, which was previously a slave of B, and promote it to the point at the A mode, even without knowing the exact replication coordinates of B. Encourage everyone to definitely go look at that, and I would love to see, I mean, really, like, the agents should end up having its own package manager, and I say this about very few things because so many things have their own package manager and shouldn't, but there should be an entire repository of fun plugins that we use for agents, and we should all be contributing to this and working on it. There should be monitoring plugins, there should be snapshot plugins, which should be able to do everything. And then we have this wonderful, beautiful GUI built on Bootstrap that it gives us a great head.
Did people just freeze for folks? Either I'm disconnected or everyone else is. Oh, okay, Shlomi's here.
Yeah, I'm back. Sorry,
Okay.
my laptop just couldn't handle the load.
Now there's 3 of me.
Yeah.
I'm growing my own DBA team right here. It's awesome.
Well,
yeah, go ahead.
yeah, John, thank you for doing the thing. Yes, so just to say, what I've got in plan for Orchestrator is, like John mentioned, I blogged about this for the past 2 weeks, like 5 or 6 blog posts. I figured out under the influence and inspiration of Sam Lambert from GitHub. He said in some forum, I just deploy, I just have this script in Ruby which compares the relay log entries, and that's how I can reattach slaves even if they otherwise don't have direct relationship or their co-master is dead or stuff like that. And I was kind of an enthusiast, and I came up with a different idea of doing it that does not rely on relay logs. And so the pseudo GDID will allow me to promote slaves across dead masters. And otherwise, if your master is dead and all your slaves are in different positions, you will be able to resync them again. And like John said, it's web, but there's web API beneath. There's nothing to the web. The web actually uses the web API, and there's command line interface. So this can actually be automated to do a master failover. All things MySQL, at least. So it's pretty exciting, and this is the thing I expect to be working on. But otherwise, other stuff like online schema changes, stuff like that, could also go through Orchestrator. So I'm very happy to get more ideas and code contribution. If anyone wants to code anything, I'm very happy to do pull requests.
So you talk about that right there, just totally brought something that I thought of. So normally, I think a lot of people here have investigated Heartbeat or other custom solutions for failover. But considering the API and command line interface, it shouldn't be that hard for the agent inside Orchestrator to actually take the complete place of Heartbeat and that entire stack right there and manipulate failovers with far more, what I would say, holistic knowledge of the cluster stack itself. And this could, I don't know if any of you have ever troubleshot Heartbeat when it doesn't work. Its logs are amazing. There's so much of them that you have no idea what to look at or what any of them really mean. And it's a fantastic, awesome tool. It's been around, and I've used Heartbeat as well. But something like Orchestrator could totally replace that with some simple agents that are really MySQL specific and could really be awesome. And so,
right. So failover is pretty complex. You have split brains and a lot of considerations to that. So that isn't an obvious thing, and I'm not I'm not keen on writing yet another group communication protocol or stuff like that, because these things,
definitely,
things are pretty much complex. So I'm not necessarily looking for a fully automated solution within Orchestrator, but it can act as, if someone else does the monitoring, or even if it's a semi-manual operation, it's enough that you're able to tell Orchestrator, okay, I've decided that this master is dead, now please fail over to another master. That Orchestrator can do pretty well.
Yeah, agreed. Totally agreed. But and with the agent functionality and the plugin functionality, that's the thing, is it shouldn't, from what I've seen of the code, it shouldn't be that hard to hook it into something like the Percona monitoring toolkit or something like that, and have it simply call out to that, to maybe not do group communication, but you could certainly have that be my monitoring system and be like, oh, look, something is dead, and it's my logic that determines what to be promoted or demoted, but it's pseudo GTIDs and Orchestrator which actually does the heavy lifting, which is generally the hard part, right? That's the really, really hard part. Detecting when something dies almost always ends up being partially business process and very specific and almost never perfect. So I don't know if I would say Orchestrator should do that, but with the agent mechanism, that's awesome. That's really powerful to be able to hook into that and being able to promote and demote on the fly without having to do, has everybody ever written those scripts where you reach out to one slave, grab the coordinates to there, reach out to another slave and grab the coordinates from there, and maybe SSH some bin logs back and forth, and before you know it, it gains sentence and nukes Russia? These things happen. So Orchestrator provides a very clean interface from where you could gather that replication info and topology information in a very standardized way, and not only that, act upon it without using, again, SSH keys and expect. That would be very cool, and I'm totally going to look at that.
Right. So again, Sam Lambert, he was interviewed at the he was interviewed at the Vivid Cortex blog, and they asked him, how is the system going to look like in 5 years from now? And he says, if you're going to SSH into a server, you're doing it wrong. right? That's the future. You don't need to SSH into anything, and especially us with with all this replication, it's like you say, we need to SSH into that and execute some commands. Then and there's a pattern to it that can be, you can't GUI everything and you can't wrap everything, but your common tasks can definitely be wrapped and simplified. So yes, and the agents are truly powerful. I started working on the agents just to solve the issue of receiving and rebuilding slaves within Outbrain. So like copy paste a slave into another. But the agent is pretty much just a courier, that can execute operating system commands on your behalf. So it can pretty much do anything. It has some parsing capabilities. So it's just a matter of saying, okay, what else would you like me to support? I mean, I don't want to be able to do RM/RF, right? But pretty much anything that's predefined and makes sense, you can wrap it up into the agent and ask for Orchestrator to communicate with it. So
exactly.
Yeah, I mean it could follow up on your system status, on your logs and stuff like that, and communicate back and forth with Orchestrator.
And that's what's so exciting about it, because I think traditionally in the MySQL world, that's been one of the hardest parts, is actually doing that orchestration. I know some people who come from more traditional databases have lamented, for better or worse, the fact that MySQL isn't like its own entire operating system into one thing. And if you look in the old changelogs, actually, back long time ago, there was actually a command called load data from master, which was originally deprecated, right? And I every now and then I go back to that page and I just stare at it dreamily and go, man, I wish that worked. And so that's being able to have a standard communication interface for just saying, I have a protocol for talking between MySQL servers that is aware of the operating system and can effectively act upon the operating system is extremely powerful. And the vast majority of my painful MySQL operational tasks are going to revolve not around actually doing the task, but how do I get the data from point A to point B, because it's got to sit in the file system before it gets to MySQL, or it needs to go talk to a tertiary central database store or NFS store or something, right? It's always, that's the painful part. It's never about well, sometimes it's about MySQL, but most of the time the operational parts are just like getting these coordinates, configuring them over here, take this snapshot, grab the file off the file system which has those coordinates and put them over here, and then do this and then jump that. And so having this consolidated, simplified, standardized interface is so powerful, so powerful, and especially the fact that it's so lightweight because it's written in Go is even better, and it's free, which is even better. And there's really no reason why we shouldn't see a library of agent functionality exploding within the community to help standardize and automate ourselves out of a job, which is all our lifetime goals, really, is to be out of work. So
cool. So I'm actually gonna pull us here because we're running over our time. And actually, I think we should talk a little more about Orchestrator next time. Hopefully, there won't be some awkward disconnects of everybody happening, and we can get a much better demo and explanation. And Shlomi, I'd actually love if you could talk a little more about the pseudo GTID stuff that you had blogged about. Cool. So, all right, yeah, that sounds perfect then.
Quick thing before we go, Shlomi, do you have a Vagrant script by any chance to bring up Orchestrator?
A Vagrant script? No, I don't.
I do, and I will have that on my personal GitHub by the next time we do DB Hangups, so that we can point at it, and every single person in the world can do Vagrant up and get their own personal Orchestrator instance. And they can
that'd be absolutely fantastic.
Cool.
Okay.
Excellent.
All right, cool. Then on that note, we'll see you guys all in 2 weeks. Thanks very much for coming today, and thanks for talking.
All right, guys. Thank you.
Thank you. Bye.
Bye.